Hey everyone, this is the recording of our TeamsCode Summer 2020 Problem Review Workshop. We went over the problems Quarantine Qualms, Courageous Colonists, and Vacuum Voyager. At the end, we also introduced our team application for those interested. Hope you enjoy! Alright, so now I'll hand it off to Connor and he can start on the first problem.
Okay, so the first problem we're going to be quickly going over today that was highly requested was Quarantine Qualms. I'm just going to share my screen. Okay. So Quarantine Qualms is medium number 1 in the advanced division and medium number 3 in the intermediate division. So if you're following along with us in the links that Wimbert sent to the chat, you can go to medium number 3 and you'll see Quarantine Qualms. So the question here is, after being in quarantine for several months, you are bored out of your mind. You decide to go outside and get some fresh air. The probability that you contract COVID-19 from anyone else outside during any given hour is 0.02 or 2%. For instance, if you are outside with 2 other people for 1 hour, the probability that you contract COVID-19 from either of them is 0.0396, which is about 4%. I'm going to go over this. I'm going to talk about why that's the case in a bit, because a lot of people had questions about that. Note that each probability is independent of the number of people and hours that you were out, meaning the probability of contracting COVID-19 from one person who was out for 2 hours is the same as that of 2 people who are out for 1 hour. Given the times in a given day that you and others are outside, compute the probability that you contract COVID-19. Okay. So first we have to, I'll just read the input and output format. So it says, the first line contains 2 integers, the hour you first walk outside, t of 1, the hour you go back inside, t of 2, and then these numbers are from 0 to 24, and t1 has to be less than t2. The next line contains the number of people outside, so 0 is less than 100, so maximum of 100 people. In the next n lines, you're given the hours that people first walk outside and come back inside. So a common misconception people had that is, if you go out with, let's say, 3 other people, then you have a 6% chance of catching it because there's a 2% chance of catching it from each person, but that's simply not the case. And the way to think about this is, if you go outside with somebody else for 1 hour, so let's say I go outside with Sean. There is a 98% chance that I will not catch COVID from him. And there is a 2% chance that I will catch it from him. So again, there's a 98% chance that I won't, and 2% chance that I will. Now, let's say right after that hour, I go out with Winbert for an hour. Now at this time, that's another 98%. There's a 98% chance that I won't get it from Winbert and 2% chance I will. So the chance that I don't have it at this point, we have the chance I get it from Sean is 0.98. And the chance that I get it from Winbert, or chance that I don't get it from Winbert, chance I don't get it from Sean is 0.98. Chance I don't get it from Winbert is, so we have there's 98% chance that I don't get it from either of them. So if we do 0.98 times 0.98, that's equal to a 0.9604. So there is a 96% chance, 96.04% chance that I won't get it if I go out with 2 different people. So the way you can calculate the chance that I will get it is just 1 minus this. 1 minus 0.9064, which is what this number is here, 0.0396. That's the chance that I will get it if I go out with 2 different people. So through that, we can deduce that the formula for figuring out what's the chance that we get out is 1 minus 0.98. So 1 minus the chance that I don't get it to the power of k, where k is the amount of overlapping hours that I have with other people. So if I overlap with other people for 10 hours, the chance that I will get, that I'll catch it is 1 minus 0.98 to the 10. So if I just type that in, calculate it right now. So there's roughly an 18.3% chance that I'm going to catch it if I go out for 10 hours. And that's the basic formula. So now that you know that it's a static number, that the chance that you get it is purely based on the amount of time that you spend outside with other people, Now all we need to do is figure out how much time is overlapping. So the way we do that is we look at the starting hours and the end hours of people, and we can just subtract the numbers. So let's say that I'm out from 5 to 12. And let's say my friends are out from, one of my friends is out from 7 to 15. Let's just say that. They're out from those times. So in this case, the amount of overlapping time that we're out is 5 hours because it's from here to here. It's from 7 to 12. That's the amount of overlapping time. And therefore, this is equal to 5 hours. And so the way you can do this is we simply look at these last two numbers right here. And we simply take a look at these first two numbers right here. And we find that we end up taking the maximum number of the first set and the minimum number of the second set. So in here, the minimum number happens to be, or so the maximum number happens to be 7. We have 7 is the minimum number. And here, the minimum number is 12. And then we can calculate it. We just do 12 minus 7 equals 5 hours overlapping. And then remember to find what we did earlier, we just do 1 minus 0.98 to the k. And this works even if it's, let's say it's a different situation. Let's say it's from like 2 to 20 and 5 to 15. Again, the overlap still happens to be the minimum of these first two numbers and the maximum, the maximum of the first two numbers and the minimum of the second two numbers. So again, we have overlap here of 10. And once we have the overlap, we just plug into the equation. So now I'm gonna briefly share my Eclipse code. I'm gonna briefly share my Eclipse code. You guys can see that, right? Okay. So this is just zoom in. Oh yeah, zoom in. Okay. So first, we're just taking the input. So we created a array to just store. This is in Java, but we're just going to go over the Java solution. But it's basically the same for all the other ones, as I mentioned the algorithm before. So first, we just want to input. So we say, okay, so I came out at my hour 0. I left at my hours 1. Then we input everybody else into an array. So others, the ith person comes out at others I have 0, leaves at others I have 1. Then we can figure out what the overlap is. And the overlap is simply equal to the minimum of the right side, the right two numbers, minus the maximum of the ones when you came out. So the minimum of when you went back inside and the maximum of when you came outside. And we add that to the overall amount of the overall overlap. With finally at the end, we simply print out 1 minus 0.98 to the k. And that's how we solve this problem. So again, for anybody who had questions about why is it 0.0396 with 2 people, again, it's just because you do 1 minus 0.98 to the k. And to find overlap, you just do the minimum of the right side minus the maximum of the left side. So that's the first problem we wanted to go over.
Hey, so I have a question. So I'm just wondering, what is import java.util.*?
Okay, so import.java.util.*, basically you mean you input everything in the java.util folder. So one of the key things that we always use to do standard input is the scanner, and that's java.util.scanner. So instead of just typing in import java.util.scanner, if we do java.util.*, it'll input everything in the util folder. And there's some time from that folder, so it just makes it easier to write it in one line.
Okay, thank you.
So the next problem that we're going to be going over is Courageous Colonists. This is medium number 5 in the advanced. I believe it's hard number 2 in the intermediate division. We'll first read over the problem. After winning the TeamsCode raffle, you decide to spend your winnings on a trip to the Midwest United States. You make up your mind to stay, and after years of grueling labor, become a well-known colonist. You have a certain amount, N of I, of sheep, wood, brick, ore, and wheat. and you want to allocate these resources in the best way possible so that you can earn the most points. In order to do this, you build a chain of settlements and cities connected by a sequence of roads in one straight line. The structures and rules are as follows. So settlement is worth 1 point. It costs 1 sheep, 1 wood, 1 brick, and 1 wheat to build. A road is not worth any points, but it is required for connecting settlements. So you can build a settlement and you have to connect it with some roads. And it costs 1 wood and 1 brick to build that. A city can be built to replace a settlement and gives 1 additional point. It costs 2 wheat and 3 ore to build. And then at the cost of 3 ore, 3 wheat, and 3 sheep, you may build a town hall to help manage your colony. And this gives you a total of 2 points, but you can only build 1 town hall. And this doesn't need to be built along roads or replace a settlement or city. Lastly, a settlement cannot be built unless it is at least a distance of 2 roads from adjacent settlements and cities. Assume that all roads are built in one straight line for simplicity. And the input format is just inputting the amount of each resource you have: sheep, wood, brick, ore, and wheat. Okay, so for this problem, basically you're given the, you're given each of the starting amounts. So let's just let me look at the sample case. This is 3, 7, 7, 9, 10. And these are actually really useful because what we're going to be doing is just when we want to try out different possibilities, all you need to do is subtract from the resources and then add points. So for example, if we wanted to build a settlement, let's say, so settlement costs 1 sheep, 1 wood, 1 brick, and 1 wheat. So the order is sheep, wood, brick, or wheat. So we can just simply subtract 1 from sheep, wood, brick, and wheat. So then what we'll end up having is like 2, 6, 6, 9, 9. And we'll have a total of +1 points because the settlement nets 1 point. So that's the general principle that you're going to be following. You're just going to be subtracting stuff from the variables and adding 1. But now the bigger question is, well, how do we do this entire thing? Like, it'd be impossible to try out, like doing all the different possibilities, doing brute force. We're probably going to run out of time if we do that. If we do it that way. So we have to think, well, what's the best way to approach this? So the first thing that we can tackle is this thing, the town hall. So again, since you can only build 1 town hall in your entire city, it's easiest to just do that first. So what we can do here is we can, so the town hall, it's going to cost 3 ore, 3 wheat, and 3 sheep. So we can subtract 3 ore, 3 wheat, and 3 sheep from our inventory. We'll add 2 points, and we'll pass that into another method to try everything else. In addition, we can also not build a town hall. So we can, because we don't know if that's going to net us the best result or not. So then we can just try passing in, not subtracting any of our resources, and just giving us, just not giving us any points. And the key to this problem, so once you figure out the town hall stuff, so you got that out of the way, now we only have to worry about settlements, cities, and roads. And yeah, the key to this problem is you by trying out different possibilities, you eventually understand that it comes down to being a greedy problem, which means that you just try to do as much as you can. So we can realize that the only things that take wood and brick, I'm not circling very well. So only roads and settlements take wood and brick to build. Nothing else takes any wood and brick to build. Therefore, we can keep going all the way. We can keep using up all of our wood and brick as much as possible to keep building settlements and roads. As long as we have wood and brick, there is no reason not to build as many settlements as roads as we can. So let's say this is a settlement, road. So we want to build 2 roads in between each settlement, right? So I'm just drawing the 2 roads like this. Again, there's no reason not to just keep building to keep building settlements and roads as much as we can. Because another thing that we also notice is that where is it? A city can be built to replace a settlement. So a city can only be built on top of a settlement. So we can't. You might think, okay, well, why don't we just go cities all the way? So maybe not spending all of our resources on settlements and roads. That might not be the best strategy, but it is always the best strategy because the city can only be built to replace a settlement. So again, we should spend all of our resources building those as much as possible. And then we can figure out the cities later. So that's the general strategy. And then each time you do that, you want to make sure that you subtract the resources necessary and add the points necessary. So I'm going to go over what the code looks like for this problem. Again, also, if you guys have you played Settlers of Catan before, this problem is based off of that. Okay. So the input for this problem is super simple. We just input 5 different numbers and we sort them into an array. And the order is sheep, wood, brick, or wheat. So in the indexes of the array, it would be sheep is in index 0, wood is in index 1, brick 2 or 3, wheat 4. So what we have to do here, so the first thing we need to manage is that town hall. Again, you can only build one town hall, so we should just get it out of the way first. And we don't necessarily know if it's going to help us or if it's going to hurt us. So this says, well, if we have the necessary materials for the town hall, if we have 3 wheat, 3 ore, and 3 sheep, then first we're going to pass into this get points method, which gets everything else with no town hall being built. Otherwise, we're going to try building a town hall, which means subtracting 3 from each of our resources that is necessary for the town hall, and then getting the number of points for and then passing in that plus 2. So we want, because the town hall's worth 2 points. So we're going to say, so first we're going to pass it into the method without building a town hall, and then we're going to be passing it into the method with building a town hall, which means subtracting from the array and adding 2 points. And if we don't have 3 of these resources, then, well, we can't even build a town hall in the first place. So we're just going to pass in 0. Now this method here, get points, tells you how many, gets through everything else. Because again, the town hall gets out of the way first, and then we can just go full on greedy algorithms for the rest. So we're gonna first put everything into a copy array because we don't want to affect the original array. And then we're gonna say, okay, so if we have at least 1 wood and at least 1 brick, then we should probably consider using as much of that as possible to build settlements and building roads. So first we test if we can build a settlement. So if we have, so we already know that we already have at least 1 wood and at least 1 brick to build a settlement, but we also need 1 wheat and 1 sheep to build a settlement. So we need to make sure that we have at least 1 of those. And last, we also need to make sure that the number of settlements is less than the number of roads divided by 2 plus 1. So the reason for this is, again, you can build a settlement every 2 roads. So this is number of roads divided by 2. And you can also build the first settlement without any roads. So then we add 1 at the end. You don't want to keep building roads if you can build a settlement, right? Because remember, roads don't give you any points. So you want to build as many settlements as possible. And then if you can't build a settlement anymore, then just spend the rest of your wooden bricks on roads and see if you can build another settlement 2 roads later. So to build a settlement, we're going to say, okay, we'll subtract 1 from each of our resources, and then we'll add 1 to this, to a variable called number of settlements. And then otherwise, we're just going to get rid of 1 wood, 1 brick, and build a road. So we've gotten that taken care of now. So now that we have, we've built all of our we used up all of our wood and brick to build as many settlements as possible by connecting with a bunch of roads. Now we have to calculate how many cities we can build. So there's 3 limiting factors for cities. So again, a city costs 3 ore and 2 wheat to build. And for that, we have to find the minimum of 3 different values, the 3 limiting factors. So the limiting factors are, first of all, wheat. If we don't have enough wheat to build a city, so let's say we have infinite ore and there's an infinite number of settlements on the board. If we don't have any more wheat, we can't build. We gotta build however much wheat we have divided by 2. So if we have 6 wheat, infinite everything else, then we can build 3 cities maximum. The next limiting factor is number of settlements. Again, a city has to be upgraded from a settlement. So if there is only one settlement on the board, even if you have infinite ore and wheat, you can only build one city. So that's another limiting factor. Last limiting factor is ore. And we have to divide by 3 because it takes 3 ore to build a city. If we have 9 ore and whatever, 100 wheat and 100 settlements on the board, we can still only build 3 cities. So after doing that, we find the minimum of these 3, which tells us the limiting factor. And then that's just the total number of cities. Finally, all we need to do is we need to return the number of settlements, because those are each 1 point. The number of cities, those are an additional point. And the number of these points, again, this came from the town hall from earlier. So the town hall was worth 2 points. So we get another 2 points if we build a town hall or not. Okay. Finally, we say, okay, so now that we've gotten that, we got points for each of those. We say, okay, now we check whichever one's higher. Did a town hall help us more, or did not building a town hall help us more? Whichever one of these values ended up producing a better result, then we want to take the higher one of those, because we're trying to get as many points as possible. And again, town hall, it could be either way. Sometimes it can help us, sometimes it can hurt us. And then we print out the maximum amount of points. And that's how you do this problem. So hopefully that helped you with Quarantine Qualms and Courageous Colonists. Now Sean is going to take over, and he's going to be talking a little bit about another one of our problems.
Yeah, so thank you, Connor, to those explanations. Connor just explained Quarantine Qualms and also Courageous Colonists. Those were the 2 of the most highly requested problems. Now I'm going to be going over a third problem, which was Vacuum Voyager. So Vacuum Voyager was hard number 2 in the advanced division, but it was also hard number 4 in the intermediate division. So let's go through this problem and see how we can solve it. So I'm first going to read the problem statement, the input output, and then go through the sample input and sample output. So a cleaning robot has been tasked with vacuuming up dust as it travels from the northwestern corner of a building to the southeastern corner of the building, given limited energy C. The building's layout is an n-by-n grid. Each room in this grid is either empty, contains dust to clean up, or contains a charging station for the robot. If the room contains dust to clean up, it is marked with a negative number E, I, J, the energy cost needed to remove the dust in the room upon entering. If the room has a charging station, it is marked with a positive number E, I, J, the energy restored to the robot's battery upon entering the room. The robot must make its way from the northwest room in the grid to the southeast room in the grid without running out of battery. E, I, J in the northwest and southeast corners will always be 0. For each room, it can only move south or east, not backwards. So before we move on, this is actually a very critical aspect of the problem, because imagine for a moment if the robot could move from any location. Suppose that it could move north, south, east, or west, then there would be no point to this problem, because there's guaranteed to be one segment where the robot can just cycle back and forth between charging stations, or maybe like a 0 and a charging station, and the robot can just gain infinite energy. Do is use a for loop and read in the grid one by one, element by element. So we actually have a nested for loop because we're reading in a 2-dimensional array. So our first for loop, we loop through each individual line, which means our for loop loops through this, and then it goes here, and then the next line, and the next, etc. So that's our first for loop. And we take that line and then call the string tokenizer. And in this next for loop, we loop through each of the individual elements and read those into the grid. So this grid I, j, integer parse in, is basically taking each integer element in there and reading it, reading into the grid. Yeah. So now what we want to do is we want to initialize our max energies at the location that we start at. And this max energy is actually going to start off as C, because C is the energy cost that is given. So max energy 0, 0 is actually the top left corner in this grid, or the northwest corner. So we initialize that energy to 5, or C. So that's what this line is. And then we do the traverse function, the recursive function that we're talking about. So let's take a look at this traverse function, because this is the main part of the problem. So before I get into the corner cases, let me first briefly explain what this traverse does. So it takes the grid as an input, which is what are the energy values in each of the rooms, and then it takes in I, which is the row number, or which row you're in currently traversing, and it takes in J, which is the column number. Lastly, it takes in this integer E, and E is going to be the energy in that room, IJ, that we see there. So before we consider these corner cases, these like optimization cases, let's first consider how we're going to do it with regular recursion. So first of all, we have max energies ij equals to E. What this does is it makes it so that the max energy at that location is going to be whatever energy that you just traversed to. And then in the next line, we traverse I plus 1, which means we go one row down. So let's say that, for example, you're at this -1 right here. The I plus 1th element would be here. So that would just be traversing one down. That's our first line. Our second line is going to be traversing one to the right. You can see that here I plus 1 has changed, but in the second line, J plus 1 has changed. So let's say that you're here again. J plus 1 would be this element here. And note that in this recursive function, you start at the starting point. You start at 0, 0. So it turns out that we're actually going to reach all the possible locations. So from 0, we're going to traverse to the right and down. But from each of those locations, we're actually also going to be traversing to the right and down. So I'm going to draw it a little bit bigger. I'll just use spaces instead of writing the actual number for convenience. So from the starting point here, you traverse down and then you go right. And then now you basically do the same thing with the recursion, except from this location, we go right and down. And then from here, we also go right and down. So then now we have 4 method calls. We go right and down here, right and down. And eventually what happens is you reach all possible locations until like every single optimal path is covered. So that's just like the way that the basic recursion works. As we said earlier, though, we have some sort of optimization. And the optimization is actually this line. If the energy is less than the max energies at I comma j, then we return. For those who don't know, return basically means that we're going to exit out of the method. So we're basically going to stop traversing because try thinking about it. If the energy at the current location is less than the maximum energy there, that means that you've already found a more efficient way to go to that location. So an example of this would be, let's pretend that you traverse the right first before traversing downwards. Then you would actually reach this -1 with cost 5 because you go to the right here, and then you have 6, and then when you go down, -1 is 5. So your max energy is 5 right now. But let's say that now you traverse downwards and then you traverse to the right. So you're here, -2, you're now at 3. And then once you're here, you basically enter the method with 2 energy. So once you're here from the traversal down and then right, your energy in this input of the method is going to be 2. But recall that your maximum energy right now is 5 at that location because you traversed the right earlier. So in that case, E is actually less than our max energy. So we're just going to return, exit out of the array, and just move on, which basically means that we don't go through that recursion because we already found a more optimized solution. So this doesn't sound like that important of a improvement, but it actually turns out that if you try to run the same 50 by 50 grid in our third test case without this sort of optimization, first of all, you may not end up with the right answer. And second of all, even if you do, it may take up to minutes, or it can take like 30 seconds, 60 seconds. But if you use this method, it'll run in well under 3 seconds. So this optimization is actually very important, and that's how we're able to run the program in time. This additional line here, if I greater than or equal to n or j greater than or equal to n, all that does is make sure that we're not outside of the grid. So if either of these is greater than or equal to n, that means that we're outside of these bounds. So like suppose that j was 4, then we would actually be to the right of that very last 2. So that means that we're already outside the grid. This is just for additional check. You actually don't need it because I already have an if statement here, but it's just so that it's easier to process the problem. So the very last thing that we do, once we've computed all the max energies at all the locations is to print out the max energy at the very last location, or the location that you end up in. And that would be at the bottom right. So we output this max energy at n-1, comma n-1, and this is going to be our final answer. Okay, so we have a question which is, can line 23 and 24 be combined into one if condition? Yes, it can. We can actually include both into one if statement. The reason that I made it in two is I wanted to make this like optimization very clear. But yeah, you definitely can shorten this code. Technically, you do not need this if statement if you're going to check in the beginning, if you're already doing this. Or if you already have this, you can technically get rid of the 23rd line and it'll run the same. I can just show briefly like that the result would be the same. So let's run this code, copying the input. And as you can see, it returns 10. Now, if we comment out this line, like so, let me save. So if you comment out this line and then run the code again, it'll also give you 10. So this code is actually, technically you do not need this line here at all. It's just like an additional safety measure. Yeah. So as I was saying earlier, this max energy is just the energy that you end up with at the bottom right. So now with that, we're basically done with the problem because all we had to do is output the maximum energy the robot can have when it reaches the southeast corner. So that's the problem. That was Vacuum Voyager, which was hard number 4 on the intermediate division and hard number 2 on the advanced division. And before everyone goes, so this is the last problem that we covered, but I also wanted to introduce an opportunity for everyone. I can see that if you're still here right now, that means you're very dedicated to your learning. So we're actually going to be, we've opened our application to everyone who wants to apply. This is for our TeamsCode team. So this means you can be doing anything from logistics to discussing opportunities with sponsors, to helping us do backend development, improving our auto grader. All these things you can help us do. Our application form was sent into the chat from Wimbert. I'll briefly just go over what each of these is looking for. So the very first thing is that you have to be either, or we're looking for primarily people in California and Washington. So if you don't live in these two locations, you can still apply, but just know that we're mainly looking for California and Washington applicants. And the grade level has to be, you're entering 9th grade, 10th grade, or 11th grade, because the reason that we're opening up the application is because right now the current team is graduating, or we're going to be graduating soon. So we need to be ready to train a new team of members. So to briefly go over what each of these roles means, logistics is pretty much the heaviest role, or it's the role that takes the most amount of, it's like the core of the contest. Without logistics, nothing else can run. So logistics would be like, for in-person contests, this could be discussing with venues, discussing like pricing with venues, looking for a good venue to be able to host everyone, what our contest schedule will look like, how are we going to be giving everyone power, or like connecting like power cables. These are all sorts of logistical roles that we're looking for. Finance and sponsors is specifically discussing stuff with our sponsors. So you'll be in Zoom meetings and emailing if you're finance and sponsors. Problem writing is basically you collaborate with the team of problem writers on our end and just write the problems. Like you can see in this case that we, so right now the problem writing team is rather small, so we're actually looking for more problem writers. The fourth thing is marketing and social media. So right now we have like Instagram and Facebook primarily, but we're planning on expanding. So marketing and social media can also mean like running Facebook and Instagram ads. So that's also part of the marketing and social media. The last thing that we have is backend development. And this is really just for long-term improvements for like future reliability. So as I mentioned earlier, the auto grader would be part of backend development, but also we have a launch test run system, which is when people can practice on our website submitting solutions. That's part of the backend development. And also we have a Learn tab, which is where you can learn skills like iOS, Swift, APCS, these things. This will all be in backend development. These two questions, why are you interested, and briefly discuss your background, they don't need to be that long. We're primarily looking for a good interview. So after, in a few weeks, or no, in a week-ish, we'll be following up with all the applicants and interviewing all of them. And the interview is really more important than what you fill out in these Google Forms. Lastly, if you have a resume, attach it so that we can have a little bit more information. This is completely not required. So if you don't have a resume, we will not count it against you whatsoever. How many contests are there in a year? So currently we have, so in all previous models, we had a Washington contest and a California contest. Sometimes we had like Oregon contests. We tried to start one in Harvard Westlake once, but that one was unsuccessful. But in general, all the contests are biannual. So we have one in March or April, and then we have another one in September or October. Due to this timeline this year, though, we're really looking for contests ideally sometime in November due to COVID-19. So that's just the timeline of our contests. So I'll answer a few questions. We'll stay on for a few minutes to answer questions. So if you don't have any questions, thank you all for coming. We really appreciate that you took this time out of your day to come and review the problems that maybe you had trouble with or you weren't sure exactly how to do. And we hope that everyone has a great rest of their day.
Hey, I have a question. So, for the application form that you just talked about, is it okay for like advanced eighth graders to apply or people in middle school? Is that okay?
So we will accept advanced eighth graders, but they have to, or ideally we're looking for people, for advanced eighth graders, like if you're going to be applying as an advanced eighth grader, primarily we're looking for people who are either doing problem writing or backend development, because for the other roles, like we have it like pretty covered by the other. But yeah, if you're an advanced eighth grader, feel free to apply. We will change our form to reflect that. And also, just for anyone who might be interested in applying, we have multiple roles. We have 5 roles here, but you can apply to more than one. And TeamsCode in general is very fluid. Kind of like our name suggests, the way that we work is not really each person does one task. We don't really give someone like, oh, can you do this task? It's more like everyone works collaboratively. So don't worry if you're interested in any of these, just you might as well check off all the boxes, because it's really, there's nothing that is restrictive here.
Also, I have another question. Where are you guys based at?
So our original organization was founded in Seattle, or Mercer Island, more specifically, Washington, but we're also based in Cupertino, California, as of the past year.
Okay, thank you.
And I forgot to mention this, but our application is due Tuesday, August 4th. So that's in, I believe, 5 or 4 days. So there's a little bit of time to fill out the application.
Cindy asks, will there be an interview required for available roles? So again, for the interview, we just kind of want to talk to you and just see like, what kind of background you have, how much time can you really dedicate to TeamsCode, and get a little bit, just hear a little bit about your personality. Again, for the roles, just feel free to check whatever sounds interesting to you. We'll be again, yeah, as Sean said earlier, one of the most important parts of TeamsCode is that we work as a team and we do everything together. So, even if you're mainly in charge of, let's say, problem writing, you're still also going to be helping in the planning the event process or helping us to find sponsors. But just you'll be more in charge of certain things. So again, we'll be working as a team. So don't worry too much about the specific roles.
And also, if you guys have any friends or know anyone who might be interested in applying to our organization, we're open to really anyone who has an interest and anyone who has the ability. So feel free to refer them to our application.
Yeah. Again, also, you don't have to be necessarily very strong at coding. Like maybe you're just an approachable person who you think you'd be good for like reaching out to sponsors and talking to them, or you're very good at graphic design and you would like to make social media posts. If you think that you have any talent in any of these areas and are also interested in making sure that you're dedicated to the team, we'd love to have you on. Yeah, don't be afraid to apply.
Also, for the briefly discuss your background or experience, if you're applying to logistics and finance/sponsors, it's very likely that you may not have any experience with this before, because like this is kind of exclusive. So for the types of roles like logistics, finance, and marketing, it's okay completely if you do not have that much experience. Once again.
I'll keep the Zoom room open for a few minutes if we have any last questions. Otherwise, everyone who's doesn't have any more questions, you're free to leave.
Thank you everyone for coming again.
So for problem writing, it actually depends a lot. Right now, we're still waiting on how many applicants we might have. If we have lots of applicants, then there would be a slightly higher level of coding experience. But in general, to be part of the coding team is just kind of for insurance, or to be able to check and fix all mistakes. Like basically, as a team, we work together to help each other like fix our mistakes. So there's not really a specific coding level, but it's preferred if you're in the USACO, silver, gold, and platinum levels. But I mean, you do not have to be necessarily into competitive programming to be able to help with our problem writing.
Someone also asked what our back end consists of. It consists of developing our auto grader, where I'm planning on moving to a website-based auto grader rather than email. And also it would consist of like redesigning our website, since right now it's not the most modern. You would also be involved in some web development there.
There's also several like quality of life improvements that we think we can do. For example, we were considering some more automated email confirmations and other things like that. But again, we haven't really finalized necessarily exactly what they're going to do. So we're going to be once we recruit you, then we have months to talk about exactly what we want to do. So. Someone asked, can I still participate in the contest if I am part of the team? Unfortunately, no, you won't be able to, because ideally you'll probably be helping us with making the contest problems. And if you already know the problems, then I mean, can't really participate in the team. However, we do recommend you get your friends to sign up, but don't spoil the problems for them. We don't want to give out the problems early.
Yeah. And part of it is because like, ideally we want people to be checking over our problems and test cases before the contest, like everyone on the team. So that's another reason why. Like if you're going to be helping out with our contest, unfortunately you're unable to participate as a contestant.
But trust me, hosting the contest is just as fun as participating in the contest. So you should definitely do that. Don't let that be a reason to not join the team, like just because you want to participate in the contest. Okay, I think the questions have. Never mind. So someone asked, does backend code the stuff that they work on? Yeah, like you'll just be like, for example, if you're doing the auto grader or working on website development, then yes, you'll be helping to code that.
Yeah, and our organization is actually kind of unique compared to other organizations in that it's very easy for you to be able to take on a much larger role, especially in our organization, than if you were to say just a member in another organization. Especially like if you join a school club, you don't have that much say in what you do. You kind of just participate in the activity that they give you. But as part of our team, you'll be part of like deciding, you'll be part of all the major decisions that we make. So this could be as significant as like what venue will we be using? What will our website look like? What problems will we be writing? So yeah, do not be afraid to join our team. Or I should put it like this. If you join our team thinking that we have a lot of people to do everything, it's not. It's more like everyone will everyone will be able to have the opportunity to do a lot or contribute a lot to our contest.
Okay. The questions have died down a little bit. So again, thank you so much for coming. This will be on our YouTube channel. If you're seeing this now, you're probably watching it from the YouTube channel. But thank you so much for coming, everybody. We hope you learned a little bit from the problem set and learned a little bit about our applications. So fill out those application forms. They are due Tuesday, August 4th. I'm not sure when this video is going to go up, but it should be a couple days. So we'll see you guys all then. And thank you so much for attending. Bye for now.
Bye.
Bye, everyone.